Okay, in this video, I am going to talk about a few things relating to exercise 9A, which is just a recap of the difference between the average and instantaneous rate of change, as well as how you can calculate average rate of change of a function in a given interval. I realized I don't have any good memes on math, so I think I need to work on that. Okay, so the first concept that we need to recap is the concept of rate of change. And this, I guess, is the foundation of the first part of calculus, which is on differentiation and derivative and all of that. But we're just going to quickly redefine what rate of change actually is. And this is one definition that you can go with. It is how fast or how slowly something is changing with respect to something else. So you're basically trying to determine the relationship between two variables. There is the first one, and then with respect to something else. Now, the classic example of rate of change that we always use when we teach this topic is the concept of speed, which is the rate of change of distance with respect to time. I really should have typed this with distance with respect to time. And then obviously another way to represent speed is if you just go distance over time. So another definition of rate of change that a lot of people use is you can think of it as a ratio between two variables. So speed is distance over time. But keep in mind that speed is not the only example of rate of change. Literally, if you have any two variables, and if one variable depends on the other variable, you can create a rate of change between the two variables. I was supposed to start rate of reaction in chemistry today. So rate of reaction is another very important application of rate of change. In this case, normally you would measure it in terms of the amount of product that you produce in the chemical reaction over time, for example. So you can see here that time is usually the variable that you're measuring it against, but it doesn't have to be. And I just want to show you one of two more examples of rates, or the word rate, that I've seen in the news in the past few weeks. And don't want to sound too morbid about things, but I found it really fascinating because we cite different numbers when we talk about death rate and then mortality rate of coronavirus, but it's always in the form of percentage. And I just mentioned earlier that a lot of people consider rate of change to be a ratio. And do keep in mind that percentage is another way to write a fraction. So 11% is 11 over 100. So you can think of this as a rate of change, and 11 will be the death over 100 people in the population. So it is still the rate of something changing with respect to something else. The interesting thing about mortality rate or death rate that is not normally mentioned when they refer to these numbers in the news, that this number, this percentage, is calculated per year, because I looked up the definition of what mortality rate is calculated, but there it's never mentioned. So I just thought that was interesting. I was going to say a fun fact, but I guess it's not that fun. Anyway, so that's rate of change. It's just how fast something is changing with respect to something else. Another term that is often associated with this topic of rate of change is the concept of gradient. So rate of change can be calculated or estimated. I think in physics, a lot of the rate of change calculation is actually an estimation. So you can either calculate or estimate it using the gradient of a graph of the two variables. So, do I have anything? Okay, so for example, let's talk about the speed example, which is distance over time. So if I want to measure the rate that distance is changing with respect to time, I could draw a graph, or try to draw a graph. Let's try again. Welcome to the comedy section of this video when I try to draw a line. Whatever. So this is time and this distance. So it is very important that you get the scale correctly, and sometimes it's really hard to know which variable is changing with respect to which variable. But obviously distance is going to depend on time and not the other way around when you're traveling. So let's say you start at 0, 0, because we went times, and then let's say that's a relationship between distance and time, and the gradient of this is going to be your speed. Alternatively, you can have a curve. Depending on what two variables you're calculating, this can still be time, but I'm just going to go with x and y here. So the gradient of this graph is going to be the rate of change of y with respect to x. Okay, so gradient is the way that the gradient of a graph is the way that you're going to use to estimate or calculate the rate of change between two variables. So that's the second word, gradient. Now, once we have the term gradient and once we start introducing graphs, we can then split the term rate of change into two types. So you either have average rate of change or instantaneous rate of change. So the average rate, I can't speak English today, the average rate of change is always going to be between 2 points. And so once again, we're going to talk about the relationship between rate and gradient. So the average rate of change is the gradient of the second drawn from the 2 points. So let's go back to this example. Let's say this is the graph of the function, and I want to find the average rate of change of y. So that's y, and this is x. The average rate of change of y with respect to x between x equal to -1, which is this point, and x equal to 0, which is this point. So this is the same as the gradient of this line, this blue line. This is the second. I think I pronounced that incorrectly, but it's essentially the line that connects or goes through the 2 points. Okay, so the gradient of this line, I don't have anything. So gradient, secant, one of those words. The gradient of this line is going to be your average rate of change between x equal to -1 and x equal to 0. Okay, so it goes back to whether or not you know how to find the gradient of a line. When you have 2 points on the line, that's really easy. You can go with your substitutes. You can go with y2 minus y1 over x2 minus x1. So that's one way. Or you can go with rise over run, which essentially is the same thing. So you're basically trying to find this distance, which is rise, and then that, which is run. The thing with this topic, I think, is there are a lot of terms that are similar to each other, and there are a lot of terms that mean the same thing. If you can visually represent every concept, I think that's an indication that you do understand everything in calculus. Because later on, once we get down to differentiation, there are even more terms. So it's very important to know the differences or the similarities between different terms. So average rate of change is always between 2 points or between a set interval. And to determine the average rate of change, you're finding the gradient of the second that is drawn between the 2 points. Now, the other type of rate of change is the instantaneous rate of change, and this is the one that we're actually more interested in. So you can think of instantaneous rate of change in the context of speed, for example. That is the actual speed that a car is traveling at, whereas the average rate of change is the average speed. So it doesn't have to be the speed at any particular point in time. So in a car, you would know the instantaneous rate of change by looking at the speedometer. Now, if you have a graph, then the instantaneous rate of change at a point, so this is a big difference. It is not between 2 points, so average rate of change is between 2 points, instantaneous rate of change is at a point, and it is going to be calculated by the gradient of the tangent to the graph drawn at that point. So it's not the gradient of a second, it is still the gradient of something, but it is the gradient of the tangent. So let's go back to this example of this graph with y and x. So if I want to find the instantaneous rate of change of y with respect to x, it's no longer between 2 points, it is at a point. Let's say, for example, I want to find the instantaneous rate of change of y with respect to x at x equal to -1. if I want to do that, then what I really am doing is I'm trying to find the gradient of the red line, which is this one, and this is your tangent. So it's not a secant, it's a tangent to the graph at x equal to -1. So gradient, so instantaneous red at, not rad, x equal to -1, that is going to equal to gradient of tangent. Gradient, can't spell, gradient of tangent at x equal to -1. Okay, so the instantaneous rate of change is the gradient of the tangent at that point. The average rate of change is the gradient of the secant drawn between the 2 points. I do want to take a minute just to recap the definition of the tangent line. This is going to be very important later on when we actually have to find the equation of the tangent. I think the first thing to know about the tangent is that it's a line. So the general form of a line is y equal to ax plus b. That's going to be useful in the future. So it's not a curve, it's a tangent line. And you can use this as a definition of what a tangent is. The tangent to the graph at a point is important. It's a line which touches the graph at that point, and that point is sometimes called the point of tangency. So I have at the point of tangency, the gradient of the graph would equals the gradient of the tangent. The graph is not the tangent, they are two different curves, if you will, but they have the same gradient at that point. I have an example here, and I will show you in the future how you can draw the tangent line using the cast. But one thing I want to point out is it is a common misconception to think that the tangent only touches the graph at one point. In order for a line to be a tangent, it has to touch the graph, but that point doesn't have to be the only point of intersection between the two graphs. So this is the tangent and this is the point of tangency. So point of tangency. But this is not the only time that this tangent line is going to touch or cross this graph. Because if I continue and, oh, this is going to be bad, but yeah, this is not working out. I really should have just elongate this before I cross it. But if you elongate this tangent, eventually it's going to intersect the graph at a point up here. But this point here, this is not point of tangency. So just because a line is a tangent to the graph doesn't mean that it only associates with the graph once. It's just that it should only have, sometimes it actually has 2 points of tangency as well, if you have 2 points with the same gradient. So I think you don't want to think of a tangent as something that only touches the graph once, but it has to touch the graph at least once. It's probably a better definition of it. So if there is a point of intersection here, it's not going to be, if we elongate both of them and they cut, this is not point of tangency. So at this point, the graph and the tangent will not have the same gradient. Okay, so that's just a quick recap of the tangent line, which we'll talk about more in the next chapter. All right, so let's go back to the two definitions. We have average rate of change, which is actually very easy to find, but the instantaneous rate of change is a lot harder, because if you look at this line, you don't actually have enough information about this line to find the gradient. So I can't really find the gradient of this red line because I only have 1 point. I need one more. So maybe it's here, for example. So in order to find the instantaneous rate of change, which is the gradient of the tangent line, the first method is by estimation. So if I look at this point, I'm like, oh, if you have a very good graph that has really good scale, you can kind of estimate, okay, so this point looks like it's around -0.5 and 1, and then you can estimate the gradient of this line based on another point. If not this one, you could potentially use this one as well. Obviously, this depends on you drawing a very good tangent line in the first place so that you could do estimation. I think in physics this is what people do, but correct me if I'm wrong. Not that you can correct me. Okay, so that's method 1. Now method 2 is to find what is called the gradient function. and then you find the value of the gradient function when x equals to -1, and that will give you, in this particular example, the instantaneous rate of change at x equal to -1. What we actually are interested in maths is how do we actually find the gradient function, because we don't want an estimation. There's nothing wrong with estimation. Sometimes estimation is the best thing that we have, but we want something a little bit more accurate. Well, think of it this way. Men and women over many, many years have worked on this field so that they convert from an estimation to an actual calculation. So we are just ripping off the hard work of many people that have come before us. I can have another 1 hour video on the celebration of the men and women of calculus in the past. Mainly men, but that's just a social society's kind of situation at the time. Let's not go off tangent. Oh, I just used the word tangent again. Okay, sorry. Method 2. So you want to find the gradient function. And in maths, we're going to focus on different ways that we could find the gradient function. And then from there, you can substitute the value of x equal to -1 into the gradient function, and that will give you the instantaneous rate of change. So let's talk about what the gradient function actually is. The gradient function is not the instantaneous rate of change, not yet anyway. So that's the first thing that you need to distinguish. The gradient function is not the instantaneous rate of change, because the instantaneous rate of change is supposed to be a number, whereas the gradient function is a rule. So it doesn't have like a, well, sometimes it is if the gradient function is a constant, but most of the time it's not necessarily the same thing. Okay, so I will talk about the difference. I think, yeah, this is not going to work out. So the gradient function, let's say if you have the function, which is f of x, I think I have to introduce some notations here as well. So let's say the function is f of x. The gradient function is going to be called f dash of x or f prime of x. I think f dash of x is the common way that we call it. And this is one working definition of the gradient function. The gradient function f prime of x, I should say f dash is, I'm going to go with f dash, sorry. The gradient function f dash of x gives the values of the instantaneous rate of change of f of x at every x values. That makes no sense. Let's say this is the function f of x. So this is y, or f of x, and this is x, okay? So we're going to go back to this point. This is x equal to -1. And then you can have this point, for example, and then this point. So every single x value on the graph of y equal to f of x is going to have a different instantaneous rate of change. So let's say at this point, x equal to -1, the instantaneous rate of change is, I can't remember what it was. I think it's like 1. Yeah, let's just go with that. And let's say at this point, the instantaneous rate of change is 0. I don't know what that is. Okay. When I draw the gradient function, so this is the gradient function. So it has the same x value, but the y value of the gradient function is going to be the red. So if you look at this, so at x equal to -1, at x equal to -1, y equal to, God knows what that is. I think that's a half. But the red is 1. So when you look at the graph of the gradient function, let's say this point has a coordinate of -1, 1. This is telling you that the rate of f of x at x equal to -1 is 1. So the y value of the gradient function is the instantaneous rate of f of x. But the function itself, it's a rule, so it has multiple points. So you can't just look at a function and say that is the rate of change at any one point. But you can look at specific values on the gradient function, and that will give you the instantaneous rate of change of the function at that particular point. So if you look at this, the rate, so at x equal to 0, the rate of change of f of x is 0. Okay, so this function, the y value of the gradient function, is going to give you the instantaneous rate of change of the original function. just ask me if you need help with this, because I feel like if I continue saying things, I'm going to confuse people more. Okay. Oh yeah, there's that. That's just what I just said. So let's talk about the difference. Is there any difference between these two? The gradient function, whereas the gradient of the tangent line, whereas the instantaneous rate of change. Okay, so let's go back to this example. If I say find the instantaneous rate of change of y with respect to x at x equal to -1. Now, you cannot, actually no, you probably can. But let's just, for the sake of the argument, assume that I give you this. So you know that f of x is -½ x squared plus 1, and then the derivative, oh sorry, the gradient function. We'll talk about the term derivative in a bit. The gradient function is -x. Once you know the gradient function, if you substitute x equal to -1 into the gradient function, it is going to give you the instantaneous rate of change at x equal to -1. So the instantaneous rate of change in this case is 1. And this is also the gradient of the tangent at x equal to -1. So gradient of this line, yes, let's annotate. So the gradient of this line is also 1. Gradient is 1. Just the gradient. So the gradient of the tangent at the point x equal to -1 would equals to the gradient function at x equal to -1. Okay, is that it? Yes, that is it for the first video. So essentially what you need to be able to do after this is to distinguish between average and instantaneous rate of change, know what gradient function is, and know the difference between the gradient function, the instantaneous rate of change, and the gradient of the tangent line. I should write that down somewhere. All right, that's it for this one.